Jonathan Martin will be discussing with us a very interesting topic, which is disseminating open source software tools for robust, smart, and accessible MRI. Dr. Jonathan Martin is a postdoctoral research fellow at the Vanderbilt University Institute of Imaging Science. He holds a PhD in biomedical engineering from Vanderbilt University. His research focuses on practical machine learning, and signal processing solutions for acquisition problems in MRI, with an emphasis on developing open source tools. Today, he will be discussing with us, like I said, on disseminating open source software tools for robust, smart, and accessible MRI. So I welcome you, Jonathan Martin, as you take the floor to discuss this topic with us.
Hi, Dorothy.
Hi.
Thank you for the introduction. Can you hear me okay, just to test before I jump into it?
It's clear. You can go on.
Okay, thank you very much for the introduction again. My name, as I said, is Jonathan Martin. I'm at Vanderbilt University Medical Center in Nashville, Tennessee. And I'll be talking about just dissemination of some software tools for open MRI. I had SMART in the title initially and was going to talk more about AI for a little while, but I think for time constraints, I decided to cut my talk back. But based on the program, I'm excited for lots of AI talks there, so it'll be covered really well. And this will be a little bit of some open source enthusiastic meanderings. I'll start with a specific open source tool that we built as a part of our lab, the Copy Toolbox Python package. I'll talk about how we've applied that to do some open source science and disseminate tools. And then I'll talk about my experiences working on a larger scale open source project, the MRI for All hackathon, which happened in New York City last year. Just incorporated a lot of really interesting open source technologies. A little bit of my biography. I did my PhD with Will Grissom in Nashville, Tennessee. And my thesis really was focused on RF pulse design. So applications of algorithms for designing RF pulses at ultra low field strengths, ultra high field strengths, kind of across the spectrum. I really get excited about RF pulses. I really think it's the most flexible part of the MRI pulse sequence. You use them for excitation of magnetization, focusing, inversion, saturation, etc. And the action, you can tailor it really nicely to be dependent on space, selective excitation, on the frequency of your spins, and to be dependent on tissue parameters like relaxation properties. So to modify the contrast. So it's this really flexible tool. And the design algorithms for pulses to achieve all of these different goals is this continual research area and kind of covers lots and lots of different applications. And in my PhD, I worked on different RF pulse design algorithms, and my advisor done that for a long time. And so kind of over the years, we developed lots of different tools for very specific problems. Parallel transmit pulse design, multi-band pulse design, some RF encoding type RF waveforms. And I think that, we had sort of, for a long time, a not fully satisfactory way of disseminating these algorithms and distributing them to the research community. So kind of our approach would typically be paper by paper. We have a Bitbucket repo with all of our source code for a particular paper here, algorithms, maybe some experiment code, most of the source all in one location. And then we move on to the next paper down the road. And okay, we're going to do a GitHub repo this time. It's going to be independent. It's going to have its own source. It's going to have its own dependencies, so whatever. And so we made kind of, I think, collections of lots of independent repositories with their own usages. They're unclear, or had case-by-case kind of variability with dependencies a lot of the times. So kind of, not, would be very difficult to merge with external projects or make work. things developed by lots of people over a long period of time. And I'll also say that for a long time, a lot of our development occurred in MATLAB, which has a lot of drawbacks. It's favored for great reasons. It's a very advanced programming tool, but it has disadvantages, and I think a lot of those stem from it being closed sourced, proprietary, semi-closed source and proprietary. So to get a perpetual license for MATLAB is several $1,000s. Outside of an academic setting, that can be a prohibitive expense to using that software tool. So if you write up all your pulse design code in MATLAB, well, so what for lots of people? And again, because of difficulty in accessing, I think it tends to only be available to a small community of developers. So you're not going to have as many people who are going to take your code and move it to their own projects or develop it further. And I think that in a lot of research areas, it in my opinion, consistently lags behind. Contrast that with Python, classic open source language and a real powerhouse of a software or of a programming language. It's free to use and adapt, unlike MATLAB. And I think because of that, has a huge development community. And in research areas like machine learning, it tends to be a dominant programming language. And I think a large part of that is because people can use it openly and freely. And so our aims were kind of to move away from these independent repositories and develop tools in an open source language in kind of a centralized way. We wanted to create an open source, something reproducible, something well tested and documented for disseminating RF pulse design algorithms. And we wanted to develop tools that could be easily integrated with other software packages. So you don't have to download a GitHub repository, figure out the usage and documentation of a new project, new code base for a new RF pulse design application. And something centralized, just a place to collect and disseminate tools. And the solution we came up with, or coming up with, is a Python package that we're calling Pulpy, Pulses in Python. It's a package for RF and also some limited gradient pulse design. I think is right there. So this is kind of a second iteration on a project that we've been working on for a bit. We started working as a part of the SIGPy project, which was a Python package for signal processing and later reconstruction. And we implemented all of these RF design tools as a sub-package in SIGPy to be able to take advantage of a lot of its nice computational capabilities. So this is a more mature second iteration where we're doing a standalone Python package that can be downloaded with the RF and gradient pulse design tools. And this, I think, has a lot of nice features, easily pip installable as a Python package. Has some really nice standard imports, nothing fancy. And then you can wrap some really popular RF pulse design tools. So for example, I'm showing using John Pauly's Python code that mimics John Pauly's SLR pulse design library using the same convention, but doing Python and applying that. And then because we have all of these other tools that are all in the same package, you can chain together pulse design functions in a nice way. So taking this same pulse that we designed with this SLR design tool and making it a multi-band pulse for simultaneous multi-slice imaging, just with a couple of simple commands rather than its own GitHub repository, and doing some simulation then of that pulse, able to chain this together with just a few lines of and so I think I hope we use this tool. I hope it's useful. And I think that the development of that is interesting. But I think something that's just as interesting in the context of these open source software tools is how to disseminate them and platforms for doing so. And as we're developing this, we're struggling with, okay, what's the ideal journal for a nice open software tool tailored for MRI uses, but maybe has some general interest. Well, it turns out there is the Journal of Open Source Software. That title kind of tells it all and checks all of our boxes. It's a developer-friendly, open access and open review journal With a code-focused review, I think it's really cool that they focus their review. The text of your abstract tends to, or your paper tends to be fairly short, and the review focuses very heavily on the actual source code and the actual performance promises that you make of your software. And so you get, as a part of the review process, these independent verifications of the functionality of the performance of what you're coding, in a way that with a conventional review, if you have a MATLAB repository that's tied onto the end of the text of your manuscript, you might not get as thorough or as complete a review. The paper review is really conversational and transparent. I think I liked. This is kind of just showing like the splash of the GitHub issue that was related to the review of my paper, and it's open on the web. If you go to this link, you can just see my conversations back and forth with the reviewers, with the editors, which I found to be, it was a very vulnerable process to have all that just open to the web forever. But I think is really nice. And this is just showing more the good, the bad, and the ugly of the review process. And so because it's focused on the code and focused on the source, you have all of these, if people will raise issues about particular lines of code that might exist. There's a nice series of checkboxes for tracking the reviewer's progress, as opposed to it being a black box of someone getting your manuscript and looking at it for 3 months and not really having any signs of life. And you get feedback. And so I just think that this is an extremely cool model for disseminating science. And it's part of a rising tide of publishing options that integrate code and source into the review. A platform that I think got talked about at ESMRMB last year was NeuroLibre. It started as a neuroscience preprint server. It's really expanded out to some other types of preprints, and has these really nice living code-based preprints. I'm just showing a screen capture here from a paper on an shimming method for the spinal cord. That was a paper that was recently published there, and they have bit by bit embedded in this preprint the code to reproduce the figures that are in the paper. And I think that's very transparent, very nice. It's just a great platform for disseminating software. And then another journal that I only just recently became aware of is Hardware X. I think this is really interesting. So their focus is on giving open source, but really for hardware projects and building projects. So they will have these interesting sections in their papers, like section 5, bill of materials summary, where they'll list out the prices, the part numbers, and even like the MasterCard links to all of the different components you need to build whatever the project is. It has build instructions, so to try and work you step by step through the design process. This really made me laugh. That the first line of that is, construction requires screwdrivers and wrenches of various sizes. Like it's like a piece of furniture you get from IKEA. They're walking you through how to build it piece by piece. And then I'm just showing a picture of the one MRI-based paper that I could identify at this journal, where they were the authors were discussing how to build an RF coil. I think this could be like this is a great venue for some MRI focused papers. So okay, I discussed building a tool, getting it published, open source, and I'll talk a little bit now about doing actual open source science with the tools that you built, with the focus being on this technology that we've worked on in our group for a little while, RF encoding. So RF encoding is kind of an answer to a lot of the problems that zero gradients have. So B-naught gradient systems have a number of drawbacks that are pretty inherent to their design. Notoriously very loud auditory noise, can have other patient comfort issues such as peripheral nervous stimulation, and they impose some real constraints on the design of your magnet. There are spatial constraints. They're having to fit inside the bore with your patient. And then also, I mean, design constraints in terms of cost. They're quite expensive generally to buy and maintain, and they require lots of support. And so for a while, people have been investigating, okay, can we encode in alternative ways using essentially gradients in RF transmit and use that as an alternative encoding rather than zero gradients. This has a number of advantages. It's PNS and noise free. It has some reduced spatial, debatably some reduced spatial constraints. I'll say this is a very developing technology, so there are a lot of unknowns about how much you can build out the geometry of these. But it has some nice physics advantages for zero gradients, negligible slow times, and a lack of eddy currents. There are constraints, however, on you're using RF pulses for your encoding that has all of the constraints that you have on any RF pulse, like heat, available power, SAW deposition, things like that. So it tends to be very more ideal for them. And there are a number of great RF encoding concepts that have been developed. Trace is one, RF phase gradient based encoding. They use a phase gradient in their B1 field to do their encoding. Another recent publication was on encoding based on adiabatic RF pulses paired with an RF gradient to do some encoding. These are really interesting applications. But one emerging technique that we've worked on in our lab a lot is using the Bloch-Siegert shift code. So the Bloch-Siegert shift is a frequency shift that is produced in response to an off-resonant RF pulse. So this off-resonant RF pulse introduces this frequency shift that is approximated by the relationship right here. The off-resonance of the RF pulses in the denominator, but the dominant thing is the magnitude of the B1 that determines your frequency shift in the numerator. And so this can give you a nice input. And this was really, I mean, the first kind of encoding that was done with this really was using it for B1 mapping. So applying this off-resonant pulse that's going to impart a phase based on the strength of your transmit field and using that to try and map, okay, where is my B1 strong, where's it? And so instead of trying to use this to just encode where your B1 field is, we're actually trying to use it to encode images, to create images. Sahibi Srinivas formerly from my lab, built a lot of really cool hardware for RF encoding. This is a wrist-sized RF encoding coil where you're designing it to have a B1 field that varies in such a way as to give you a nice linear phase variation across space. And she was able to demonstrate really nice phase encoding. Was working on frequency encoding with this. So you can see kind of the phase wrap across this linear phantom that she was able to achieve, and able to turn that into encoding of a resolution phantom on the right, substituting this axis of encoding for a B0 axis, which is really cool. But my particular research question that really fascinated me was not the phase encoding or the frequency encoding, but slice. Like, how on earth do you perform slice selection if you don't have a B0 gradient to localize your excitation? That's like a critical part, right, of the two ingredients that you need to perform a slice selection. Is a slice select gradient and a frequency selective pulse. And we had this idea, this isn't the focus of the talk, just to give a general idea of applying this off-resonant RF pulse that creates a frequency gradient with B1 as opposed to space, and adding to that a frequency selective RF pulse. So take these two different RF pulses, kind of smack them together, and you'll get a slice selective, an excitation selective with B1 rather than space. And then if you have an RF coil, just look at that slides. You have an RF coil that has a B1 gradient that turns into a spatial slice. So, okay, this is kind of maybe an obscure RF pulse design topic. Why am I talking about it? Well, we really, I think this idea kind of manifested from having this nice open source toolbox, PolPy and SigPy before that, SigPy RF before that. So because we had all of these design pieces of design code that had their own nice, consistent Python code that could all be mixed and matched together, it lent itself to this idea that was really just taking these two different classes of RF pulses, smacking them together, and making them into a pulse. So I think that having a nice tool that can maybe be compatible with a few different algorithms for whatever your MRI area is can make a big difference in terms of new research ideas. And this is just showing, and it's something that gets investigated, I think, a lot at ultra low fields where you don't have these concerns about SAR heating and power constraints as much. And we're just able to use them for slice selection, so just showing some experimental slides for that. And so, okay, this was kind of, we built this one tool, we are able to actually apply it for doing new science, creating new things. And then I should say also we, created this new RF pulse design tool. We built that into the toolbox. So it's now something that exists inside of there. And the final thing I'd like to talk about is when all of these open source tools can kind of come together at a larger scale. I was a participant in the MRI for All hackathon in New York that happened last year. It was an event that really brought together a lot of really cool open source technology. And so I'd just like to talk about that for a few minutes at the end of my talk. As I said, this was in October 2023. It was hosted by NYU Langone. And about 50 scientists and engineers all participated. And I was a part of the acquisition software team. So trying to not bother ourselves with reconstruction or UI, but just work on making hardware control for running pulse sequences happen, essentially. And our objective was to develop an open source MRI scanner capable of determining the contents of a mystery object, some unknown phantom with an unknown content that we were trying to determine the identity of. And this is just a couple splash slides of what the kind of overall design of the magnet looked like. It had this fully 3D printed casing and structure to it. It was really nice. All the CAD files are up online at a link that I'll show later. And the design was based on a Hallbach magnet design. It had these many individual magnets that were numerically optimized into an array and then transferred to CAD software, made this very nice homogeneous field inside this about this size scanner. Just a couple fun building of the magnet slides from the main web page. This is piecing together that Hallbach array in individual rings to create the full body of the magnet. And some scenes from the gradient construction. So they had these 3D printed gradient inserts, and we're just able to line coils into groups that were 3D printed, and super groove clamp, epoxy, tape, and you go. My focus, the area that I was helping with was acquisition software, which I'll just talk about a little bit because I think it's a great example of a lot of open source tools coming together for one product. So we used the red Pataya as a controller for the scanner. And the open source software tools that we were using were PyPulseSeq and Marcos for calculating our sequences, designing our pulse sequences, and then Marcos would execute those on Pataya. And then through the development process, we used this tabletop scanner on the Martino Center provided for testing or software acquisition without having access to a physical magnet because it was being built at the same time. It was something that we were trying to do all of this in parallel. And as a part of that, something that was a really critical ingredient was having a nice virtual machine, a virtual environment that we could have all of our development tools available in and continue development. And then all the development for this console, for this acquisition software, all happened in Python. And you can find where all the GitHub code for that is. This link. Marcos was really one of, and Pulseek were Pulseek, the Python version of Pulseek, were the real backbones for this project. So this is a shot from the Marcos documentation. It integrated Pulseek for sequence design, and then this Marcos client server setup for calibrating and setting up the sequences, and then translating that to control the board. It's a very cool library. And kind of, again, like having a virtual machine, having this nice development software allowed us to do a lot of things without having access to the physical magnet as it was being built. So we would have this stand-in magnet that was kind of similar to what we were trying to get to, used a Repetaya, and we're able to do all of our development in this virtual machine. And then with a Repetaya, simulate that, what we would try and achieve on a control scanner. And the acquisition tools that actually got developed, just kind of showing a couple slides from that. Acquisition integrated with 2 other software teams. There was a group working on the UI, along with the fancy console based console display, and then obviously a team dedicated to reconstruction, but we worked on developing, basic calibration sequences, frequency calibration, gradient strength calibration, so on and so forth, some imaging sequences, and then calculation and visualization of the trajectory. This is a video that was recorded by Anis Artigas of actually using the console and kind of running through some of these acquisitions and calibrations. So this is kind of the process of loading in a scan, with first creating a patient, loading in a scan. There's this really nice UI console that was developed where they could modify sequence parameters, so on and so forth. Skip through all of it. Let's keep running in my time. But then after acquiring this acquisition, kind of standard conventional scroll capabilities to go through your stack of slices, visualize case-based magnitude here in the middle, the phase of the image of the right. And some nice capabilities. Okay, we're designing all of these pulse sequences in PyPulseek. We're actually doing some visualization of the elements in the pulse sequence. It's pretty cool. And so all of the software, all the files and components that are needed for the design of this magnet are all at the GitHub repository. And just to conclude, at my end, I would just encourage you to build and maintain your own open source tools, something that is specific to whatever your own expertise area is. And then I would encourage you not only to build them, but then battle test them with a review that if you can find it using one of these journals that is software intensive and user dependent, relying on people actually using the software. And I think I really would argue that having well-developed modular software tools can pay big dividends in research, can help you come up with new research ideas by getting the tools that you might not have had access to before, and make large-scale projects and collaborations possible that wouldn't have been possible otherwise. And I'll just thank all my collaborators and especially the MRI for All organizers and team members that worked on that project.